All right, we're back. While you were learning how to deal with arc links, I was learning how to deal with video editing, which took quite a bit longer than I expected, but I think we're rolling. All right, so just to remind you, you had in-class question, and you were given this parameterized curve, right? R cosine theta, R sine, or R sine, sorry, R cosine t, R sine t, right? Which we know makes a circle. And if we take the integral from 0 to pi over 2 of the length of the velocity vector, right? So if this is x of t, right, then actually let's do that before we set up the integral. Let's go ahead and calculate an actual formula for this. Right, so x prime of t is r minus r sine t r cosine t. So when we take the norm, or the length of x prime, I won't go ahead and write it down. What I want you to notice, well, let's see. So this is going to be equal to the square root of essentially r squared sine squared t plus r squared cosine squared t, right? And this simplifies to the square root of r squared, which is equal to r. So we actually have a constant, right, a constant length velocity. And we learned that, right, and so we learned that this tells us, right, the direction of x tells us the direction, right, of our velocity. And this tells us a magnitude of this velocity. So to get arc length, what we want to do is start integrating the magnitude of the velocity as we go along the curve. So as we set up this integral, right, so our integral right here, right, that I just highlighted in green, right, so I want to calculate the length of the purple, this purple part of the curve, and I've set this up as the integral from t equals 0 to t equals pi over 2 of the length of x prime dt, and I just showed you, right, why this reduces to a constant, and we can see here that we get r times pi over 2 when we do the integration and plug in the endpoints, right? And this matches what we already know, because if we were to go the entire way around the curve, right, the whole curve has length 2 times pi times r, and we only went around a quarter of the way. So 1/4 of the way, right, is just 1/4 of this. So in this case, right, we have exactly what we have here, which is r times pi over 2. We just divided this quantity by 4 to get that. All right, so that's a very simple case, right? And you can do that one easily. Now the second two questions where we're asking about these curves, 3et, e to the t, 4e to the t, and the line are related. Okay, so let's go through those. Right, so now my x is 3e to the t, 4e to the t. My velocity, which is equal to my x prime, if I differentiate this, I just get 3e to the t back. And if I differentiate this, I get 4e to the t back. And so the length here of x prime, and I set it up so that you'd have like a 3, 4, 5 triangle, right? So if you go ahead and plug this into the length formula, you'll get 5e to the t, right? So that, right, is the length of our velocity, right? So it's related to that scaling term that we use to go between time parameterization and arc length parameterization. Okay, so if I want to calculate the arc length itself, right, what I need to do is take the integral, and let's see, I gave you from 0 to the natural log of 2, right, of this quantity, and that reduces to the integral, right, of this quantity, 5e to the t dt. I know how to integrate this and plug in the limits. So what this is going to be is 5e to the t, taking out these limits, right? And so here, when I plug in this guy, right, I get e to the ln2, so that's 2. And then I subtract off what happens when I plug in 0, right? So I get e to the 0, which is 1, times 5. So the answer you should have got was 5, right? Now remember this, we're going to get essentially the same answer for the other, for the final function. And what I want you to notice is that here, my new function, right, I'm going to erase the e to the t's. I'm going to put in t's instead. And I'm going to carry this, actually I'm going to put them in a different color so you can see exactly what it is that I'm changing from one problem to the next. Okay. So instead of e to the t, right, I have 3t and 4t. Now when I go to calculate the derivative, it is now constant. When the parameterization was based on using this exponential function, right, this derivative was not constant. Now it's a constant. Now go ahead and look over at your slides. And what you'll notice, if we zoom in a little bit, is that we have, right, these functions plotted relative to one another. So here I have the first function, right, which is, or sorry, the second function is 3 times t. So the one that I have up right now is 3 times t, 4 times t. And you can see that that makes a line, right? So that makes a line that's tracing here from the origin, right? And you can see that it joins with a blue line, right, somewhere far up the curve. And in fact, right, that blue curve was the other function we were looking at, where we had the exponentials here. In other words, that function that looked like, right, an exponential function traces out a line, but it traces it out at a different speed than the linear way we can trace it out, right, just using this parameterization in terms of time. Does that make sense? Right, so in the exponential parameterization, the longer we go, the faster we're going, essentially. Okay, so but for this problem, we have our velocity, or sorry, our position vector is 3t, 4t, right? Our velocity is a constant 3 times 4. Now, right, so I'm just going to put a little empty box to show that I erased something. Okay, and now when I take the length of this, right, I erase that bit, and I set up my integral, and now my integral is not from 0 to ln2, but the corresponding points on the curve. So when it was an exponential, we went from the point 3, 4, right, to twice that. So here, I'll leave this up, right, and you can see that we'll get the same number out of the integral. So here, right, if I wanted to plug this in, right, a time point of 0, I would get 5 here, which is what you're going to get if you plug t equals 1 into this equation. In other words, like our lower limit for how we're parameterizing this section of curve, right? Instead of going from time 0 to ln2, we're going from time 1 to time 2. So this is e to the ln2, right? And this here is e to the 0. In other words, right, the endpoints that I have for this integral. Okay, and in this case, right, instead of integrating this function 5e to the t dt, we're just integrating a constant function. All right, and we know that we can evaluate this as the function 5t with the endpoints 1 and 2, right? And I plug in 2 and I get 10, and I plug in 1 and I get 5. And so you can see that this calculation that we just did, right, is essentially the same calculation we did for this other parameterization of the straight line, and we got the same answer, right? In other words, we have computed the arc length for one example where we trace out the line with constant speed, and here we've traced out the line with variable speed, and we can see in each case that the length of the part of the curve that we trace out is length 5. All right, so let's move on. So now we are going to move from arc length derivative, right? Arc length derivative. So let me rewrite the formula for you. Actually, let me back up 1 second, right? Because we worked for a little bit. This tangent vector is our arc length derivative, and to get that, we differentiate the position, right? The position vector with respect to arc length. And we showed that we could get that by taking the time derivative, in other words, the time velocity, right, and dividing by its length. So in other words, I have this vector, this unit tangent vector, and I showed that that was derivative with respect to arc length. So to compute this operation, differentiate with respect to t, divide by velocity. Okay, now we're going to do that operation twice. We're going to differentiate with respect to t, divide by velocity, and then we're going to differentiate again and divide by velocity again. All right, and that's going to give us something called curvature. All right, so curvature as a vector is defined, let me get this all erased for you. Right, curvature, and we call this kappa, as a vector is defined as the derivative of our unit tangent vector with respect to our arc length. Now, if you remember, right, t itself was defined in terms of arc length in one of our definitions, right? And so this was the derivative of position with respect to arc length. So we're going to first, right, calculate t, and then we want to calculate the curvature kappa, right? This tells us the direction of the derivative. This tells us, this is like the rate of change in the position vector. This is the rate of change in the velocity vector, right, in this tangent direction. So in each case, we can use what we know, right, about derivatives and say that dt ds should be dt d little t. So the derivative of tangent with respect to arc length is the derivative of tangent with respect to time, right? And then we can multiply here by the derivative of time with respect to arc length. Right? And that's a general formula. We can do the same thing here. And if you recall from before, dt ds was 1 over the length of the velocity vector, right? So 1 over the length of x prime. So then we can put all of this together, right? We know how to we can take a time derivative of t, we can take a time derivative of x, and then these adjustments to change between the time derivative and the arc length derivative are the same for each derivative that we take, right? So the correction term that we apply for differentiating with respect to a different variable, the correction term we apply is the same whether we're taking the first derivative to get t, and then we differentiate again, so we're taking a second derivative to get kappa, and the correction term, right, the correction term here is the same in each case, and it's this 1 over norm x. All right, so putting it all together, we get this formula here. To get kappa, I'll write it out on the board. To get kappa, okay, so let's start with, right, we're starting with x. So what do we do to x? We take, right, our first thing that we do is we're going to calculate t. So we're going to differentiate t with respect to arc length. Or sorry, we're going to differentiate x with respect to arc length. Oh, I'm sorry, with respect to time. We're going to apply this operation. We're going to differentiate with respect to time, apply the correction factor, and then we're going to do it again. We're going to differentiate with respect to time and apply the correction factor, right? So when we do it the first time, we differentiate x with respect to t, and then we apply the correction factor. And now we're going to do it again. We're going to differentiate this, right, with respect to t, and we're going to multiply by the correction factor again. In other words, we have another constant multiple of x prime that goes in here, right? So this is just something you calculate one time. Okay, it looks slightly different than how it's written, but essentially the same as what we have here over in your notes. So I'll re-highlight it again in pink. So now you can see it in pink. So that's the formula that we just derived here. And again, we just applied the same operation twice. Differentiate with respect to t, multiply by this correction factor. Do it twice and you have curvature. Oh, it looks like our movie is ready. So that's part 1 of our movie. That will be ready to upload, but I've got to keep going with the lecture. All right. So maybe I will take another quick break and let you, I'll do that while you do some problems. All right, so here, all you're going to do, right, is apply the formula to get kappa, right? So kappa, differentiate with respect to t, right? Correct. Differentiate with respect to t and correct. Okay, so kappa is equal to the correction term, the norm of x prime, times derivative with respect to t of the derivative of x with respect to t, right, times our correction term. All right, so go for it, and I will get your other video uploaded.